Hello, everyone. If you are studying IGCSE Computer Science 0478 Paper 1, this video series will help you revise each topic more easily. We'll go through chapters 1 to 6, practice questions like those from the past papers. This will help you understand the types of questions you will see in the exam and how to answer them. These videos are designed to support your learning, build your confidence, and help you to get best grades you can. So let's get started and make your revision count. In this video, we're going to discuss the three topics. The first topic is binary shifts, second topic is binary additions, and the third topic is two's complement. So let's get started. So let's discuss the first topic, which is binary shifts. Question 27, state the type of binary shift used by a computer to multiply or divide binary numbers. The binary left shift is used for multiplication, and binary right shift is used for division. The binary numbers, this one is a number stored in a random access memory RAM. Give 8-bit binary number that will be stored after the shift has taken place. A logical left shift of 3 places is performed on the binary number. So now we know that it's a left shift and it's a 3 places. So how we perform the left shift, 3 places? So first of all, we just need to delete the 3 numbers from the left side and then add 3 zeros on the right side. Okay, so add 3 zeros on the right side, and that's when we get our answer. So this is our answer after the left shift of 3 places. Let's see the next question. A value is stored as a binary number in a register, and this is the number. A logical right shift of 3 places is performed on the binary number. Complete the binary register to show its content after this logical right shift. So this is the binary number, 8-bit binary number. Now we need to remove the 3 numbers from the right side, or 3 bits from the right sides, and then add 3 zeros on the left side. Okay, and then we'll get our answer. So this is our answer. Question 30, binary number. This one is stored in an 8-bit register. State the effect of performing a binary left shift operation on this number. So what is the effect of performing left shift? A logical left shift by 1 position will multiply the number by 2. The 1 left shift multiply by 2. 2 left shift multiply a number by 4. 3 left shift multiplies a number by 8, and 4 left shifts multiply a number by 16, while the 5 left shifts multiplies number by 32. Question 31, a binary number. This one is stored in an 8-bit register. State the effect of performing a logical right shift operation on this number by 3 positions. A logical right shift by 2 positions will divide the number by 4. So 1 right shift divides the number by 2, 2 right shifts divides the number by 4, 3 right shifts divides the number by 8, and 4 right shifts divides the number by 16, and 5 right shifts divides the number by 32. Okay, now let's see the next topic, which is binary addition. 2 8-bit binary numbers, this one and this one, are to be added together using binary addition. Add the 2 binary integers and show your answers in binary. So before adding those numbers, let's review the rules. So rule number 1 says 0 plus 0, sum is 0, carry is 0. Rule number 2 says 0 plus 1, sum is 1, carry is 0. Rule number 3 says 1 plus 1, sum is 0, and carry is 1. Rule number 4 says 1 plus 1 plus 1, sum is 1, and carry is 1. So let's now add those numbers by keeping those rules in our mind. So 0 plus 0 is what? 0. 0 plus 1 is 1, no carry. 0 plus 1 is 1, no carry. 0 plus 0 is 0, no carry. 1 plus 0 is what? 1, and no carry. Now we have 1 plus 1, which is what? Sum is 0 and carry is 1. So sum is 0 and carry is 1. Again, we have 1 plus 1, and sum is what? 0 and carry is 1. And now last one is 1 plus 0, and it will be 1. So our answer is this number. Okay, question 34, 2 8-bit binary integers, this one and this one, are to be added together. Add the binary integers using the binary addition and show your answers in binary. Okay, so this is the rules that you need to keep in mind. So let's start adding those numbers. So 1 plus 1 is what? 0, 1 carry, 1 plus 1 again, 0, 1 carry, 1 plus 1 again, 0, and 1 carry. And now we have 3 1, 1 plus 1 plus 1. So we know sum is 1 and carry is 1. Again, 1 plus 1 is what? 0, and 1 carry, 1 plus 1, 0, and 1 carry, 1 plus 1, again 0, and 1 carry. So now we have 3 ones, which means sum is 1 and carry is 1. So we add, and then we have 1 carry. But as you can see here, we got a carry beyond the last bit. Okay, so we have 8 bits, and the carry is beyond the 8 bits. So there is no more space to store 8. This is called an overflow error because the result is too big for the register to store. So this is the overflow error. Okay. Now, question 35. The two binary numbers are added by a computer and an overflow error occurs. Explain why the overflow error occurs. So an overflow error occurs when the result of a binary addition is too large to be stored in the allocated number of bits, causing the loss of most significant bits. So that's the definition of the overflow error. Now let's see the two's complement. Okay. So question 37, state the name of method commonly used to represent negative numbers in computers. So that's called the two's complement method. Okay. Or more precisely, signed numbers. Okay. Signed numbers are usually represented using the two's complement method. A computer system uses two's complement to represent signed integers. State the purpose of the sign bit in two's complement binary numbers. State what it means when the sign bit is 1 and the 0. So the sign bit indicates whether the number is positive or the negative. Okay. So if the sign bit is 1, it indicates a number is negative. If the sign bit is 0, it indicates that the number is positive. Okay. So now we have this number can be stored as a two's complement integer. Convert the two's complement integer, this number, to binary and show all working. So now we need to convert this number, which is in two's complement, to binary number. Okay. So now we know it's a two's complement number. So this is the last bit or most significant bit is called the sign bit. And this is the sign bit. So 1 is our sign bit. So in this case, the most significant bit is minus 128. So let's add the numbers together. So we had the power of 2 and the last power is minus 128. We add the number underneath those one and we add them up. So 32 plus 2 plus 1, we got what? 35. So now we need to minus 128. So minus 128 plus 35, and we got our answer minus 93. So this number is equal to what? Is equal to minus 93 in binary. Question 40, the binary integer minus 32 is stored as two's complement integer. Calculate the two's complement integer that would be stored. So now we need to convert this number into 8-bit two's complement. So first of all, you need to ignore the sign here, okay, and convert 32 to binary. So this is the binary of 32. So you can see here 32, 1 here and all zeros. Okay. So it's the 8-bit number, just like we have 2 zeros here. Next step is to flip the bits. What I mean by flip the bits? So 0 will become 1 and 1 will become 0. So here you can see this 0 became 1, 0 to 1, 0 to 1, 0 to 1, 0 to 1, and this 1 becomes 0. And then we need to add 1 in this number. So 1 plus 1 is what? 0, and 1 carry, 1 plus 1 again 0, 1 carry, 1 plus 1 again 0, and 1 carry, 1 plus 1 again 0, 1 carry, 1 plus 1 again 0, 1 carry, and 0 plus 1 is 1. And then we can just write 1 and 1 as it is. Okay, this is our answer. So this minus 32 is equal to this number in two's complement. So that's it.